Welcome back. This video is going to cover photoelectric effect and get into the Bohr model and also the calculations dealing with energy and light. First of all, let's talk about the photoelectric effect, which kind of was a driving force to understand what was going on with the interaction of light and electrons. So it was the photoelectric effect is just defined as that electrons are emitted from a surface of a metal exposed to light of a minimum energy. If the light did not have enough energy, the electrons were not emitted or given off, and a scientist, Max Planck, proposed that the metal absorbs and emits energy in small specific amounts called quanta. Vocabulary word. Quantum, which is singular of quanta, be like cactus, cacti. Well, this is quantum, and the plural is quanta. And a quantum was just defined as a minimum quantity of energy that can be lost or gained by an atom. And a line spectra of elements was different from what we would consider the electromagnetic spectrum. A line spectra for an element was just a unique spectrum that contains only certain wavelengths that element could emit based upon being bombarded with light of different energy levels. And each element has its own unique spectrum, which you can see in your textbook that everyone is always reading, of course. And this was one of the early indication that light, besides being energy, also can behave as a wave. So, when we last left off with the atomic models, which was in the Rutherford type of thing, where, if you recall, Rutherford did the gold foil experiment, and he found that the atom was mainly empty space. You had a small positively charged nucleus, and then you had electrons that were orbiting outside the nucleus. Now, that was a pretty good atomic model, but it didn't explain certain things. And that was kind of what was driving the scientific community to kind of figure out, okay, we've got a pretty good atomic model, but we're not there yet. Because just like an example we may have talked about in class is like if you take a blacksmith, if you go to a blacksmith and you notice that he heats up, let's say something iron and in a forge, and then he takes it out and it's glowing. And the atomic model had no explanation for that. Because remember, that's not a chemical change. That's a physical change. That the iron has absorbed energy and is now glowing. So what was puzzling to scientists is what is going on in the atom that is allowing this energy, this light, to be released. And so Bohr came along, and he studied the hydrogen atom, almost exclusively, just because it's the simplest, so that you can try and, if you can get some understanding of hydrogen, the atom, and how it behaved, then you would be able to extrapolate those results onto more complicated or complex elements. That the electron in hydrogen, because remember hydrogen only consists of a single electron and a single proton, it absorbs and releases energies only in certain amounts. So an electron can gain energy and get excited to a higher energy level, called an excited state, and then the electron can then release the energy as light when it returns to the ground state. And the energy emitted corresponds to the frequency observed in the hydrogen specific spectrum. And that's what we're talking about a little bit above, this line spectra of elements and the unique spectrum that each element possesses. So in Bohr's model of the atom, it again built upon what Rutherford had, but he just said an electron can circle the nucleus only in allowed paths or energy levels. And here we have a picture of the hydrogen atom and Bohr's model. Right here in the very center is the nucleus. And these concentric rings, actually no, this whole thing is a nucleus. Then here's the energy levels. And this is just depicted like the first three. And if this is the hydrogen atom with one electron and then one proton and maybe a nucleus in the nucleus and maybe a neutron if it's deuterium or tritium. But this electron here can gain energy and get promoted to either this energy level or the third energy level or higher, so on and so forth. And then once it's in this excited level, well, it's eventually going to release that energy back down, give it off. And that is what this here is kind of showing, is that once it drops down back to the original level, this energy here, this that is absorbed, is released as light. So the equation for this is pretty straightforward. The energy is equal to H, which is a constant, times nu, which is the frequency. So energy is the energy absorbed emitted. The letter that looks like a lowercase v, which is the lowercase Greek letter nu, is the frequency of the radiation. And H is another constant, which is on your back of your periodic table. And it's a very small number, 6.626 times 10 to the negative 34th. And here it's joules times seconds is what the unit is. Joules times seconds. And where J represents the joule, which is the SI form of energy, or the unit of energy. So we can also do some now practice problems with this equation if we want to see how frequency, wavelength, and energy are related. So if we want to calculate the energy of a quantum of radiant energy, which just means light. Light is radiant energy with a frequency of 5 times 10 to the 11th seconds to the minus 1, and you automatically realize that is just hertz. If we want to calculate energy, that's easy. We just don't even have to rearrange our equation because we're given the frequency here. So the setup is going to be this Planck's constant. 6.626 times 10 to the minus 34th joules times seconds times the frequency, which is 5.00 times 10 to the 11th, and it's 1 over seconds. All right, so you can hopefully see that this seconds and this seconds cancel out for unit perspective, leaving us just with joules, which is what we want. And then I just have to plug that into the calculator. 6.626. And we get 3.313 times 10 to the minus 22nd. We have to apply our sigma figures. Planck's constant is from the periodic table, and it's a defined constant. So we just go off the 3 sigma figures for the frequency, which is 3.31 times 10 to the minus 22nd joules. Next problem. Threshold photoelectric effect in tungsten is produced by light of a wavelength 260 nanometers. What is the energy of this photon in joules? And we're given a conversion because nanometers is not a unit of metric prefix you're required to know. So 1 meter is the same as 1 times 10 to the 9th nanometers. So this problem, if we want to think about how we're going to get there, is we want energy. And as we talked about above, energy is Planck's constant times the frequency. Well, do we have the frequency? No, we've got the wavelength. But we can use the first equation from this section because this relates frequency and wavelength. So this problem here is going to have several steps. 3 steps, to be honest. The first one is we need to take the 260 nanometers and convert it into meters because we can't use nanometers. And here's our conversion factor, dimensional analysis. 1 meter goes on the top, the 1 times 10 to the 9th nanometers goes down here so that our units cancel. Right, we can't forget the dimensional analysis. We put this into our calculator. Oops. We put that in our calculator correctly. And we get 2.60 times 10 to the minus 7th meters. Second step is, now that we have, and this is the wavelength, we've got to convert this from wavelength to frequency. We're going to use the first equation to do that. Right? If we want to figure out the frequency, that is just going to be c over wavelength. So speed of light 3.00 times 10 to the 8th divided by that 2.60 times 10 to the minus 7th. We put that into our calculator, and if you do it correctly, you should get about 1.15 times 10 to the 15th hertz, or 1 over seconds. And lastly, we can now solve for energy because we've got the wavelength and we know Planck's constant. So that's 6.626 times 10 to the negative 34th joules times seconds. Seconds here and there cancel, leaving us just with joules, which is what we want. And we should get around 7.63 times 10 to the minus 19th, give or take. 3 same figures because we started with 3. This 260, see that decimal place there, that dot? Telling you that last 0 is significant. All right, so that was the Bohr model. Bohr model still wasn't where we wanted to be. It didn't still cover everything. I'm not going, this is where the mathematics and the theory start to pass into much higher level particle physics and quantum mechanics. And so for first level chemistry, we're just going to kind of talk about some of the key things. Is that a gentleman, de Broglie, was one of the folks that was proposed that electrons act like a particle and like a wave. And so you can apply some of the formulas that calculate energy, frequency, and wavelength used for light to also electrons. Then you had the Heisenberg uncertainty principle, which he was using the photons of light to try and detect electrons by attempting to locate a specific electron by aiming photon light at the electron, which, if you just even take a minute to just think about that, about what he was trying to do here, taking a photon of light and attempting to locate a specific electron by using this photon of light. would not be easy to physically do. But he came up with something called the Heisenberg uncertainty principle, saying that it is impossible to determine both the position and velocity of an electron at the same time. This was kind of a lead up to what you've probably heard of, this gentleman called Schrödinger and the Schrödinger's cat type of thing, and the whole field of memes that spawned. So in the quantum mechanical model, Schrödinger was basically using probability as the basis to describe the behavior of electrons. And this model altered the Bohr model a little bit, where the Bohr model was saying that, hey, you've got these electrons in certain energy levels that they're kind of fixed. You know, it's kind of like almost like a solar system type of model, where you've got the planets that are orbiting the sun in fixed orbits. Well, the quantum mechanical model kind of threw that out. Is that, you know, the allowed energies an electron can have and how likely or probable it is to find an electron in various locations around the nucleus. These, instead of energy levels, they're basically called atomic orbitals. These atomic orbitals, where they were able to be, these electrons in a particular energy level, to be able to be found. Okay, so an atomic orbital is just defined as a region in space around the nucleus in which there's a high probability of finding an electron. These electrons are also classified as being in certain energy levels, which describes how far the electron is from the nucleus. So it's given a whole number, 1, 2, 3, 4, 5, whatever. 1 is closest to the nucleus and has the lowest energy. A sublevel just corresponds to one or more orbitals of different shapes. And these shapes were dependent upon the probability and statistics that you'd be able to find them there. And there's 4 main types of sublevels that we know of. S orbitals, which are spherical in shape. And right here, the one on the top, that is an s orbital, and it's a sphere. It's in 3 dimensions. You see the x, y, and z axes listed here, and there's only one possible s orbital. So in an s sublevel, there's only one orbital. P orbitals are basically called them like a dumbbell in shape. And there's 3 orientations, and there's 3 orbitals for p sublevels, and you can see them over here. And they look like dumbbells. On yours, it might be kind of hard to see. There's a sphere here, and there, and there, and there. So you've got these dumbbells that one is on the z-axis, one's on the x, one is centered around the y. The d orbitals are the next one. There are 5 possible in the d orbitals, and I understand that as we're talking about this today, this is probably making no sense to you. But what these sublevels represent is the likelihood or the probability that you will find an electron in that region of space centered around the atom, because at the center of all these axes, the x, y, and z, that is the nucleus. D orbital, those things are clover leaf in shape. You can see them here. There's there's these 4, and then there's this one that's kind of more toroidal in shape as well. And lastly, there's the f orbitals, which all you can describe this shape as is complex. There's 7 possible. Now, what I've attached here, this is basically the first couple energy levels and their sublevels kind of superimposed. In the center is the nucleus. The blue sphere you see there is the 1s energy level. The slightly larger reddish sphere that fully encompasses the blue sphere, that is the 2s. And then you see these three orbital shapes, those are the 2p. You notice they're all superimposed on each other. So if you have an electron in a 2p orbital, it could, if at any given point, be in the same region of space as like a 2s or a 1s. But these are the shape or the areas or the locations where those electrons are most likely to be found for each of these energy levels. Now, if this was to continue and we added the 3s, you'd be a bigger sphere. The 3p, which are going to be these bigger dumbbells superimposed on these things, and then you can start adding, the d orbitals superimposed on this. You notice it's going to get real complicated real quick. And that's unfortunately the nature of electron configuration, is that it's not as simple as we may have hoped it to be. But just to sum up or review things, if we're just looking at the first several energy levels, what sublevels can be present? In the first energy level, the only thing you can have is an s sublevel. In the second energy level, you can have an s and also a p. Third energy level, you can have the s, p, and d. And lastly, in the fourth energy level, you can have an s, p, a d, and an f. So what this is telling you is that as you go up in energy levels, the first one you can only have the S sublevel. The second one you can add the P. Third one the P and the D, and the fourth is where the F sublevel orbitals first shows up. And yes, if you go into the fifth energy level, conceivably there's going to be another sublevel possible. However, none of the atoms that we have, none of the elements have enough electrons to actually start to fill what could conceivably be past the F sublevel. And whatnot. So one thing to keep in mind, each orbital can hold 2 electrons. So if we want to look at our sublevels a little bit more closely, in the S sublevel, there's only 1 orbital present. Right? We talked about this kind of up here. S, you only have 1 orbital. P, you can have 3. D can have 5. F can have 7. So that means the total number of electrons that can exist in an S sublevel is, if there's only 1 orbital and it holds 2 electrons, it's 2. In the P sublevel, if you have 3 electrons, 3 suborbitals, each one can hold 2. That's 6. A D can hold 10, and an F can hold 14. So we will get into more practice with doing electron configuration in class, and we will do an activity in class that will hopefully make this a little bit easier for you to understand and grasp.